Okay, so today we're going to be starting our chapter about exponential functions. And so what does it mean to have an exponential function? It's a function that has a letter, the x, the input value, as the exponent. And so we're going to be talking about that bit by bit for the day. So let's first practice doing exponents. So let's remind ourselves of, you bring things to powers, what does that mean? And we just took a test about fractional exponents, right? And so, we've done, say, 8 to the 2/3, where remember the denominator tells you what root you're taking and the numerator tells you what power to bring it to. So if you have a fractional coefficient exponent, you could say, okay, well, the cube root of 8 and then square it. Okay, that's what we have to do. So it'd be 2, and then 2 squared will give us 4. Now, if this had been negative, you would take the cube root of 8 still, and then you'd square it. And then the third task is make it into a reciprocal. So it'd be 1/4. Okay, so as you look at these, remember 8 to the 0, what is it? It's 1. 10 to the third is 10 times 10 times 10. Do you know how to do that without a calculator? Well, it's a 1 with 3 zeros. Okay, so just practicing, how do you do this? 2 to the negative 3 means 2 to the third, which is 8, and then do the reciprocal of it. So it'd be 1/8. This means take this to the third power and then flip it over. So if you bring it to the third power, you can either think of taking 1/8 times 1/8 times 1/8, or you can say, I'm going to take 1 to the third power and 8 to the third power, which would give us 1 over, let's see, 8 times 8 is 64. 64 times 8. You got to make sure you know how to multiply this here. So that gives you 32. 6 times 8 is 48. So it'd be 512, pardon me, carry that. And so because of the reciprocal, you would do the reciprocal of your answer, so it would be 512. Okay, so the exponents tell you what power to raise it to, and the exponents, if it's negative, say do the reciprocal of your answer when you're done. So 10 to the negative third means bring 10 to the third power and then do the reciprocal, so it'd be 1 over 1,000. And then the last one says take 0.3 to the third. How do you even do that? Well, 0.3 times 0.3 is 9. We're like, do you remember how you do this? Remember that the answer to a multiplication problem has the number of decimals to the right of the decimal point as the number of decimal values to the right of it in the problem. So there are 2 to the right of it in the things you're multiplying, so it's going to be 0.09. And if you times that by 0.3 again, you're going to get 27. You need 3 decimal places, so it's going to be 0.027. And so you'd get the same answer if you did 3/10 times 3/10 times 3/10. You'd get 27 thousandths, and that's how you read this value as well. 27, and that's in the thousandths place. That's the tenths, the hundredths, and then the thousandths. So 27 over 1,000, or 0.027, which is 27,000. So it's interesting to see, numbers do have a lot of logic to them, and the things you've learned do layer up. And so if you've got any questions, come on and see me. We can chat about this, or you can Google it. Either way is fine. The next thing is, assume I've got one piece of paper, and I'm in class. I'll hold up one sheet of paper and be like, okay, if I've got one sheet of paper, and if a single piece of paper, if you just lay it on a desk, is 0.0038 inches tall, okay? And so let's double that, okay? So if I double that, like I put 2 pieces of paper on each top of each other, how tall would that stack be? Would be twice as much as one sheet of paper. So if you double that, you get 0.0078, okay? Well, what if you double that again? Instead of having 2 sheets of paper, you have 4 sheets of paper, okay? And then, so that means that would be twice as tall as 2 sheets of paper. So that would be 0.0152, okay? 2 doublings. Okay, and say that you had 8 sheets of paper. You could technically fold papers in half as you're doubling it, or just get it twice as much paper. And so the question is, if there's 8 sheets of paper, how tall would that be in inches? That would be 0.0304 inches, okay? And then if you have 16 sheets of paper, okay, would be 3 doublings would be 8 papers. 4 doublings would give you 16 sheets of paper. So twice as much each time. So that would be, you can double that pretty quick, 0.608 inches tall. Okay, my question is, if you doubled your single sheet of paper 25 times, you're like, okay, you went from 1 to 2, and then 2 to 4, and then 4 to 8 sheets, and 8 to 16, 16 to 32, 32 to 64. If you doubled it, did twice as much as the one, 25 times, how tall would it be? Would it be as tall as the building? Would it be as tall as your desk? Would it be as tall as like an airplane? How high would that be? Okay. And you can I would ask kids to be like, and most kids will be like, probably as tall as this, the school or something like that. And so the question is, okay, go ahead and figure it out. And I'll walk around the room and I'll ask kids to figure out what that would be. And if you want to think about it in positive video, you're welcome to as well. Be like, okay, well, how many inches tall would your stack of paper be if you start with 1 and you just double it 25 times? Okay, how would you figure out what that is? And, you could take 0.0038, and you're going to times it by 2, okay? Because every time you double it, it gets twice as big. So you do times 2, times 2, times 2, times 2, but that does get repetitive. You got to double it 25 times. How could you put that in your calculator without having to do times 2, times 2, times 2, times 2, times 2 so many times? Well, you have a button called the power, and that helps you be like, okay, if I want to times it by 2 25 times, that will help us do that, okay? And so if you put that in your calculator, you're going to get this 127,506.84 inches. And you could divide that by 3 or by 12 to get how many feet it would be, okay? And then you divide that by 12, you get 10625.57 feet. And if you divide that by 5,200 yes, 5,280. I joked for a second. And so 5,280, so divide how many feet, this many feet by 5,280, you're going to get about 2.12 miles. It's kind of crazy, isn't it? So 2.012, I forgot to know. So, can you write an equation to model this this situation? Well, height based on the number of doublings, okay? Or you can just say, the height equals. Okay, let's just do that. So the height is equal to, you start with 0.0038 and you double it ever many times you want to. Maybe it's 25 times, okay? And so that would be your equation. Okay, if you just double it 3 times, you would times it by 8. If you double it 4 times, you times it by 16, okay, because it would be 16 sheets of paper. So it's kind of an interesting way to start writing an equation. These are called exponential because the variable's in the exponent. The next thing is, let's practice graphing these. And I think the big thing is, do you remember how powers work? You're like, I don't know, I'm not so sure. All right, well, let's practice. Do you remember 2 to the 0? Okay, so this says if x is 0, what would you get? So you plug in x is 0, you get 2 to the 0, that would give us 1. Okay, let's do this one, 2 to the 1st. Okay, if x is 1 in this function right here, let's do 2 to the 1th. Okay, well, it's just 2. How about 2 to the 2nd? Well, it's 4. And then 2 to the 3rd. So type in x is 3, you're going to get 8. And I want you to do this without a calc, okay? How about 2 to the negative 1? Okay, well, that's 1/2. Because 2 to the 1th is 2, and then flip it over, you get 1/2. So 2 to the negative 2, you have to bring it to the second power, which is 4, and then flip it over, you get 1/4. And then 2 to the negative 3rd is 2 to the 3rd, and then flip it over, you get 1/8. So as you graph this takes some effort. 0 is 1, 1 is 2, 2 is 4, 3 is 8, okay? 4 would be 16, okay? Negative 1 is not negative, it's just going to be 1/2. Negative 2 is 1/4. This is an 8. The thing is this, will it cross the x-axis ever? The answer is no. And there's something called an asymptote, which is normally on the x-axis for exponential function, unless it's been vertically shifted up or down, okay? So the asymptote is going to be, no, there's an asymptote. That's how you spell asymptote. ASYMPTOT. Okay, and I don't know why I made it plural, but let's get rid of the S at the end. There's an asymptote there. And so the asymptote is actually the line, the x-axis, which is going to be the line y equals 0. Okay, that's the asymptote. And so it will get infinitely close the more negative you go. So, but it's going to be never cross that, as long as it's not shifted up or down. So the growth is constant. It's doubled each time, okay? And so it's increased by 100% each time. And so, so it's doubled. And then what's the domain and range? The domain is negative infinity to infinity. That's the domain. And the range is from 0, not including 0, to infinity. What is the y-intercept in y? So that means 0 is 1. And y, it's kind of a weird question. If you plug in x to 0, you get 1. Okay. And I guess that's kind of as far as deep as I'm going to go. Okay. How would this differ from our paper folding problem? Well, how is it even the same? So let's think about this. Notice these are actually parent and child relationship. What are you even talking about? Look at this. Do you see how this is y equals 2 to the x? The child of this is going to be 2 to the x, but have a vertical compression by 0.0038. So the number in front of the function, if the parent function is 2 to the x, it is a vertical compression by 0.0038. And so if you graph this on the same graph, you will see 0, doublings is going to be just 0.038. Okay, 1 doubling, I should get a pen out instead of a marker. 1 doubling, pardon me, is going to be, what do we get? 0.0076. And then you're going to get a little bit more. 2 doublings is going to be 0.0076, pardon me. We can plot these points, and the truth is, it's not going to be very big very quickly, is it? Okay. But eventually it's going to get up to all those miles, isn't it? Okay. And so, if you have doubled it 7 times, it's still going to be 0.4864 inches tall. Okay. And so it will eventually, echo this. Okay. Now the negative doublings don't make sense. Okay. And so, but it's going to be a vertical compression by 0.0038. Okay. So that's kind of cool. The next thing I would say is, we're going to practice looking at transformations first, and then we're going to practice graphing some of these. So let's do that here. Over to page 2. We're going to talk about, is it an exponential function or not? So if it has a variable as the exponent, your input value variable, then it's going to be exponential. Okay. And then if it's going to have not, then these would be examples of not. This is cubic. This is linear. This is going to be quadratic. And those don't have a variable, the input value variable x as the exponent. So those are not exponential functions. So these are yes. And then these are not so much. Okay. The second thing is the parent function of all these is going to be a value to the x power. Okay. That's going to be it. Now there are multiple parent functions. You could have 3 to the x power, 4 to the x power, and those are all parents. And then they have children, that can be shifted left or right. So basically the parent is going to be all the ones that have the same b value. Okay. So just like on the previous problem, the parent was 2 to the x, and one of the vertical compression children was be 0.0038 times 2 to the x. Okay. And so you got to watch to be like, do they have the same nose? I mean, do they have the same b value? Okay. The one that's holding up the x. If they have the same growth or decay factor, then they're going to be children. Okay. And so here's something I want to say is this. So look for matching b values. Okay. And that unites the family. It's like having the same last name. So it could be 5 to the x. And the child would be 2 times 5 to the x. And so we'll talk about that in a sec. But I want you to know that if b is greater than 1, it will be growing. Okay. You'll notice it'll go uphill. And then if b is between 0 and 1, you'll notice it's like a fraction. You'll notice it'll be falling. Okay, it'll be decaying. And so let's watch that B to say, are they an optimist? They're going uphill, or is it going downhill? Let's see what that family does. And so So here would be the transformational little chart, okay? So if you have the original function, that's b to the x, the children would be as shown. The a part coefficient here is going to be a vertical stretch or compression. That's the coefficient in front of the original function. So a would be a vertical stretch or compression. And then also if it's negative coefficient there, it would reflect it vertically. Okay, so if a is negative, it reflects it vertically. If you want to shift it left or right, that's going to be the h value, the value by the x. Okay, again, if you have x minus 3, it's going to go right 3. If it's x plus 5, it's going to go left 5. So adding and subtracting to the x coordinate, which is going to be in the exponent, will shift it left or right. And then, of course, the vertical component, if you add or subtract to the function, okay, which is going to be b to the x, it's going to be shifted up or down, okay? So there are other things we can do to it. So those are the primary things, okay? So look at this. This next equation is going to be, is it growth or decay? Well, it's actually going to be decay because think about the parent of this function would be f of x is equal to 1/2 to the x. And the base there, that b value is between 0 and 1. And so therefore, you'll notice it's falling as it goes from left to right, okay? And so the a is 8 is a vertical stretch from its parent. Okay, and so it's a little bit weird to be thinking about all these families. Like the next one, the parent function is going to be f of x is equal to 3 to the x. Okay, and so from its parent, it's going to be a vertical stretch of 2, is going to be right 1, it's going to be down 1. Okay, and so the parent matches the growth factor, okay, or decay factor, which is the b. And so the letter C, the parent function here is going to be f of x is equal to 3 to the x. And so that'll be a growth. And from its mom, it's going to be up 1. Okay. And then this function is going to be f of x, its parent is going to be 1.03 to the x. And so that'll be growing because the base, the thing that's holding up the x, if you think about like cheerleaders, the bases hold up those little flyers and the flyer is the little x. Okay, and so that base is bigger than 1. So you'll notice the graph will be growing as you travel from left to right. Okay, now when we say growing, we're assuming there's not a whole lot of reflections and things like that. So we're talking about just like kind of the positive, non-reflective things. So the parent function will be decaying on this first one because it's a decay factor. So look up here one more time. We've got if you've got b to the x and b is between, is greater than 1, it's going to be growing. If it's between 0 and 1, it's a fraction, it's going to be decaying. And let's talk about why, okay? Think about this, okay? This first question, as we make a table of values, okay? You can start with x being 0, okay? We're going to do some negative as well. But if you start with x being 0, let's think about what that does. I'm going to go over here and do it. You're going to do 8 times a half 0 times, okay? So you do 8 times, well, half to the 0 is just 1. So 8 times, none of times. So it's just going to be 8, okay? So if you plug in 0, you get 8. If you plug in 1, okay, you're going to take 8, you're going to times it by 1/2 to 1 time, basically. So a half to the first is just 1, and you're going to take 8 times a half, and half of 8 is just 4. Okay. And then you're going to do it twice. Okay, well, let's make some room here because I'm running out of it. Okay, so if I erase some of the stuff. So if I do 8 and I times it by a half twice, okay, you can do it times a half twice, or you can say, well, let's take a half squared. Well, half squared means square the 1, square the 2, you get 1/4. And you're going to times it by 8, or 8 over 1. 8 over 1 times 1/4 is going to be 2. Notice you're basically taking 8, starting with 8, and you're timesing by a half multiple times and saying, okay, so 1 was 4, 2 was 2. What do you think is if you plug it into, you times it by half again? Okay, it's going to be 1. So if you made this a 3, that would be times by 1/8. And so 8 times 1/8 is just 1. Okay, so think about what we're doing. And so what if we did -1? Okay, let's try that. It's a little scary. 8 times a half to the -1. Well, to the -1 means raise it to the first power and then flip it over. So flip over the half, you get 2. So 8 times 2 will give us 16. So it does follow the pattern. It's just really weird to be like, hey, the next one would be 32. We've got this graph that's decaying by a half each time, okay? If you've done half-life in chemistry, you'll notice, yeah, we do decay by half. Now, it'll never go below the x-axis here, so we're going to draw an asymptote here and say the asymptote is going to be the x-axis, the line y equals 0, unless it gets shifted up or down. So domain and range, the domain is negative infinity to positive infinity, and the range in this case would be from 0, not including 0, to infinity. Okay, so we're looking at, okay, and we can even talk about end behavior. As x goes to negative infinity, the graph goes to infinity. As x goes to positive infinity, the function goes to 0. Okay, so it's kind of weird to talk about, what is this graph actually doing? Okay, the next one. Again, the parent is 3 to the x, so it's going to be growth because the base, the thing that's holding up the x, is going to be a number bigger than 1. And so we're tripling it each time. Okay, so there's a lot going on here. That's why we've got a couple days to kind of work through this. So what I want us to do is let's plug in a couple of values, and let's start with, I'm trying to think. Compared to its mama, it's going to be vertical stretch by 2. It's going to be right 1 and then down 1. Okay, so I can start with 0, but since I'm going right 1, starting with 1, that kind of is a good thing to do, okay? And then plugging in, say, 2. This is kind of like the starting value. And then we can plug in negative 1 and kind of see what's going on there. So let's try this. So if we plug in 1, okay, I'm going to start with that because the graph appears to be moving right 1. So we do 2, and then we go 3, and then we have to do 1 minus 1, which will be 0, and then we subtract 1. Now let's do PEMDAS. 2 times 3 to the 0, well, do the power. 3 to the 0 is 1. And so if you do 2 times 1, that's 2, and then you subtract 1, you just get 1. So 1 is 1. It's very interesting. Let's plug in 2. Okay, so you do 2 times 3 to the 2 minus 1 is 1, and then subtract 1. So we'll again PEMDAS. 3 to the 1th is 3, times it by 2 is 6, and 6 minus 1 is 5. So 2 goes to 5. Okay, and then you could plug in 3. We could do 2 times 3 to the 3 minus 1 is 2. Minus 1, so 3 squared is 9 times 2 is 18 minus 1 is 17. So it gets really big really fast, doesn't it? Okay. Okay, and so we can graph that and be like, okay, great, let's stick this on here. Oops, I need to get a pen. And then if we plug in 0, okay, so plugging in 0, we're going to do 2 times 3, and you do to the 1 minus 2, so that's negative 1, and then we're going to subtract 1. Now it's going to get fractional, and we got to try not to cry too hard. So 3 to the negative 1 is 1/3, okay? So we have to do 2 times 1/3, okay? That's 2/3, because you put this over 1, so 2/3 subtract 1. Can you do 2/3 minus 1? It's negative 1/3. Okay, so it's negative, or so 0 is negative, is going to be, yeah, negative 1. You're like, wait a minute, Kinzer, you told me it's not going to go below the x-axis. Well, let's think about it. The 3 to the x won't, but what does this graph do? It's right 1. It's a vertical stretch by 2, and it's going to be down 1. Okay, so our asymptote is not on the x-axis. Our asymptote literally is at the line x equals negative 1. And so we're going to be graphing this, and it's going to kind of be like an airplane that's taking off from left to right. It's growing, okay, because the growth factor is a number bigger than 1. That's the 3. And it's going to be as shown. Okay, and so you got to like make sure it shows the graph. But if you know, hey, it's right 1, well, then start at 1. Okay, if it's left 5, we'll start at negative 5. Okay. So start there and then move left and right of there a little bit to get, so you get the trademark shape. Okay. Notice graph A is decaying because the growth factor or decay factor is 1/2. Notice letter B is growing because the growth factor is 3. Okay. And so it's growing because the thing in the parentheses, the thing that's holding up the X, is going to be bigger than 1 or smaller than 1. Okay. So, The next one, the parent is still 3 to the x, and so, but it's going to be up 1. Okay, so let's see if we can do this. Okay, so if we look at this, 3 to the 1, and it's up 1. Okay, so it's not shifted left or right. So we are safe to start at 0 and go to 1 and 2 and like say -1 and see kind of what it looks like. But we can draw the asymptote right here. It's just up 1. And I will ask you to draw the asymptote because I want you guys to know what's going on here. You know, what are we doing? And so we're going to plug in, let's start with 0 because it's not moved left or right. So let's do 3 to the 0 and then add 1. Well, that's 1 plus 1, that's 2. Okay, 3 to 0 is not 0, it's 1. Okay, so we do 1 plus 1 is 2. And then if we plug in 1, we do 3 to the 1th, which is 3, and then add 1, you get 4. And then let's see what else we got. 3 to the 2nd, because x is 2, and then add 1, that's 9 plus 1, that's 10. And then if we plug in -1, we do 3 to the -1, and then we add 1. Okay, 3 to the -1 is 1/3. 1/3 plus 1 is 1 1/3. Okay, so you can kind of see where we're headed here. 0 is 2, okay? 1 is 4. 2 is 10. It just gets out of control really fast. And then -1 is just 1 1/3. So it's still above the asymptote. And you can see what's going on here. The domain is -infinity to positive infinity. The range is going to be from 1 to infinity, not including 1. Okay, so domain, -infinity to infinity. The range is going to be 1 to infinity. And behavior would be as, remember that, as x goes to infinity, your function goes to infinity. As x goes to -infinity, what's your function do? It goes to 1. F of x goes to 1. Okay, so it can go towards a certain value. Okay, because it's not going to go to -infinity. It's going to go to 1. So it's kind of weird what we're doing here. So from its mom, it is just up 1. Okay, and so you could graph 3 to the x. And I do want to see the tables you're making, and I do want you to practice doing these. There will be times where we use a calc. Like on this next one, of course, we're going to use a calc. Okay, and so the parent of this is going to be 1.03. Now, it's growth because this value, okay, the exponential growth factor is going to be bigger than 1. Okay, it's just by a skosh. You know, if it was 1, it would not be growing or decaying. But since it's 1 and a smidge, okay, if you take 500 and you times it by 1.03 repeatedly, bit by bit, it will get bigger and bigger. Okay, so if you start with a number and you times it by a number smaller than 1, like half of it, it's going to take half of it each time. It's going to get smaller and smaller and smaller. And so exponential functions are repeated multiplication. So you got to make sure you know, start with 500 and then grow or decay from that point by timesing it repeatedly by that growth or decay factor. So if we start, it's not moved left or right from its mom. So it's going to be starting with 0. You would do 500 and then you do 1.03 to the 0th power. And so that would be 500 0 times that you times it by that, or 500 times 1 is 500. Now, of course, this graph is not exactly measured. So we can just call this 100. We can call this right here 200. We can call this 300, and then 400, and then 500. And so we can say, okay, if you times 500 by 1, you stay at 500. Okay, but if you do it one time, you're going to get, what do I have here? 515. So you do 500 times 1.03 to the 1th, okay? So you take 1.03 times 500 one time, and you get 515. So you're like, okay, awesome, okay? It's up a smidge. And if you times it by 500 times 1.03 squared, or 500 times 1.03 times 1.03 again, you're going to get 530 point something, okay? So you'll notice it is, growing, okay? And it's a vertical stretch compared to just plain 1.03 to the x, okay? Vertical stretch by 500. And so the domain is this is -infinity, positive infinity, and the range is going to be from 0 to infinity. So this actually is a basic growth factor. The x-axis is still going to be this. It's just going to take a long time till it hits there, okay? That's going to be the asymptote there, okay? So what I want you guys to realize is a couple of things. Exponential functions have the variable and the exponent. Their growth, if the base of that exponential factor is going to be bigger than 1, they're going to be decay if that exponential factor, the number that's holding up the x, is going to be a fraction smaller between 0 and 1. And so, and that's evidenced by, if you take a number and you times it by half repeatedly, the more times you take half of it, the smaller it's going to get. Okay, if you're like, that $1 billion, we'll take half of it and throw it away, you're going to have sequentially, quickly less and less and less money. Okay, and so, and the more transformations, the harder it is to predict your next point. But if there aren't too many, like on this first one right here, you start with 8 and you're just taking half of it repeatedly. And so it goes from 8 to 4 to 2 to 1 to a half, etc. And so knowing how to deal with exponents can do PEMDAS, raise that value to the power, and then times it by the coefficient. So make sure that you do PEMDAS as well. All right. Well, thank you so much. Have a good day.